Right, in this video we dig a little bit deeper into section 16.3, which is work integrals in the context of the fundamental theorem of line integrals, essentially saying that a vector field f is the gradient of some function phi called a potential function. Okay, and if we know that the vector field has a potential function, then it makes doing line integrals quite a bit easier to do. Okay, so what we're seeing in this example on the right is a vector field, right? That if you choose certain points P, Q, and R, for example, maybe S, many points, that we have the vector field, and we can see that this vector field is pointing towards the center, okay? And here is a formula for the vector field uh, given as, and can be thought of as a force field, okay? And this force field is, the formula given is a variant or um, a precursor to the gravitational vector field. Okay, so if this is our vector field F, then we can see that the magnitude of the vector field comes out to be 1 over x squared plus y squared plus z squared for this vector field in three-dimensional space. And x squared plus y squared we know is equal to rho squared in spherical coordinates. So what we can imagine here is that we've got a point, and emanating out from that point are a series of spheres of various radii, and the strength of the vector field um, varies by 1 over the distance from the center squared. Okay, so essentially what we're seeing here is the inverse square law. Okay, that gravity drops off as 1 over the distance from where the mass of an object is concentrated. Okay, and this vector field is important not only for its physical significance as a gravitational field, but if we check it, this function phi here is equal to 1 over the square root of x squared plus y squared, which is given in spherical coordinates as 1 over rho, right? This potential function, if you were to take the derivative of it, the gradient, by phi x, phi y, phi z, would in fact come out to be this force field given as the gravitational force field. So this is an important example of why we are using vector fields and the potential function, is because some of the most important vector fields are actually vector fields that actually have a potential function. And what's important in this example is that if we try to have an object, perhaps that's in orbit, like a satellite that's in orbit around an object like the Earth, right? That we could ask, what is the amount of work done by the vector field on that object as it moves around its orbit? Okay, and what's interesting here is that if you're asked to do a line integral, okay, along this curve, and you start and end at the same point, so this object's in orbit, for example, this probably should be an elliptical or a circular orbit, I'm just drawing it like this, but that you start and end at the same point, because this vector field is the gradient of a potential function, and that potential difference, the phi at point P minus the phi at point Q, because P and Q are the same point, that the difference of these is the potential difference at the same point, and therefore you get 0. Right? So we have, for example, in this case, a gravitational vector field is what's called a conservative vector field, which means that there is a potential function for it. And therefore, if any of your curves or your paths that you are integrating along to find the work start and end at the same point, then you know that the amount of work done will be equal to 0. Okay, so here is a very important vector field, and the fact that it is conservative and the fact that we actually know a potential function for it is incredibly important. Okay, so in the remainder of this video, I would like to look at just maybe an example that doesn't have as much physical significance, but notice that we have a vector field given in this problem. Okay, and that vector field is x squared y cubed y squared. Okay, and we know that there is a potential function for this because it has been given to us, and you can actually check that this is a potential function by the gradient of it. When you take the partial derivatives with respect to x and y, you get x squared y cubed y squared, which is equal to the function vector field f. Okay, so if we were asked to compute a line integral along this curve C, which is this part of the circle, and you start and end at the same point, right, then we know that the line integral along the curve, where the curve is the full circle, and you're going around counterclockwise, right, because you start and end at the same point, and because the vector field is actually a gradient of a potential function, then the potential difference, phi at P minus phi at Q, is going to come out to be equal to 0. Okay, and so it's really easy, what we call the right-hand side of the fundamental theorem of line integrals, okay, to compute the potential difference, that comes out to be equal to 0 pretty easily. This potential difference is a very important result because the left-hand side of the integral, or doing the definition of the line integral, might lead to a very challenging integral. Here's the integral you're going to get if you try to compute the line integral along a circle. Here's your curve r of t, right? If you find the vector field along the curve, okay, and then you compute the vector field along the curve dotted with r prime at t, you might get a hard integral that you have to compute. And so it is nice on the left-hand side to be able to compute that left-hand side integral by using the right-hand side part of the fundamental theorem of line integrals. Okay, so here we've seen the importance of the fundamental theorem of line integrals and this potential function for evaluating a line integral. And so everything rests on finding this potential function. Okay, and the question of how do we know that a given vector field actually has a potential function. Okay, so in this remainder, the last part of this video, we will just discuss how do we know that a vector field has a potential function. And then in another video, we will look at finding the potential function. So here's an important result called the test for conservativeness. There are a lot of synonyms in this section. So this is a test for the conservative nature of a vector field. Okay, and essentially what that means is that if a vector field F is given to you, is there a test to figure out that this vector field actually is the gradient of some function phi called a potential function? Okay, so we notice here that if the vector field is the gradient of some function phi, then we know that the first entry of that vector field has to be equal to the partial derivative of the function phi with respect to x. And the second entry of the vector field needs to be the derivative of the function phi with respect to y. Okay. So this is what it means. This is the meaning of whether or not a vector field is conservative. It just means that there is a potential function for it. Okay, and this is the definition of what it means for a function, vector field, to have a potential function. So now we'll notice that because we know, whoops, sorry, let me unlock the screen here. Okay, because we know that we can take partial derivatives, okay, we know that if you take the partial derivative of the first entry of the vector field with respect to y, and the first entry of the vector field is equal to the partial derivative with respect to x, then if we take a partial derivative of f1, we'll get two derivatives of the potential function phi. But if you look at the second entry of the vector field and then take its derivative with respect to x, we will get the derivative of the function phi with respect to y and then with respect to x. Okay? And because we know that the partial derivatives in different orders come out to be the same for nice vector fields that we'll see mostly in this section, then we know that this implies that f1y is equal to f2x. Okay? So this is the criteria right here to determine if a vector field f, which in this case is a vector valued function in two variables, and a vector field in two-dimensional space. A vector field is conservative, okay, aka has a potential function phi. A vector field is conservative if f1y is equal to f2x. Okay. So if you look back at all the other vector fields that we have found a potential function for, we've done this example here. Here is a potential function. We knew this was a potential function because we checked it, right? But you'll also notice that this vector field, the first entry of the vector field is x squared y cubed. The second entry of the vector field is x cubed y squared. When you run the test for whether or not there was a potential function, f1y is equal to x squared 3y squared. And the derivative f2x, partial derivative of this function with respect to x, is 3x squared y cubed. So f1y was in fact equal to f2x. And it was this criteria here that the test was passed. So we now know that there was actually a potential function. And we knew there was a potential function because we found one. Okay? What we're setting up for is to run the test to see if there actually is a potential function, and then we will go through and find it. So only after the test is passed will it be real beneficial for us to go looking for one. Okay? If you look at this other example that we did, the vector field was equal to 2xy, the first entry of the vector field. f2 is equal to x squared minus 1. If we run the test to see if this vector field is conservative, f1y is equal to 2x, f2x is equal to 2x, and so f1y was equal to f2x. So we know that there is a potential function for this vector field. And we also knew that there was a potential function because we found one. We've demonstrated the existence of one right here. So what we're going to need to do in the next video is to, on vector fields that actually pass this test, figure out how to actually find a formula for these potential functions. And that will be the subject of the next video.